Hello everyone, welcome to my channel. This is Dr. Fan. Graphical representation is a big part of AP Physics 1. And today I'm gonna use one practice problem to help you understand the key graphs in 1D kinematics. Okay, let's get into it. We have solved this question mathematically in a previous video, but today we're gonna look at the graphical representation of this motion. So the question says a ball moved towards the east with a velocity of 3 meters per second. A stable wind blowing to the west gives the ball an acceleration of 1 meter per second square in the first 2 seconds and an acceleration of 3 meters per second square for another 4 seconds. And the first part of the question asks us to plot the velocity versus the time chart for this motion. Well, to plot the velocity versus the time chart is not very straightforward, but we can easily plot the acceleration versus time chart. So if we plot acceleration versus time chart, we can do something like this. If we set going to the east, going to the right as our positive direction, so my acceleration in the first 2 seconds would be a1 equals to minus 1 meter per second square, because this acceleration is going to the west. So the curve would look like this. And for the next 4 seconds, the acceleration is minus 3 meter per second square. So this is my acceleration from 2 to 6 seconds, and which is minus 3 meter per second square. This is minus 1 meter per second square. So this is my acceleration versus time chart, which is very straightforward. So how does this help us to plot the velocity versus time chart? Let's do it. So if we draw the velocity versus time chart, the first thing we can do is that we can find the velocity at the very important instance. For example, we can find the velocity at 2 seconds. How do we do that? We can use the kinematic equation v1 equals to v0 plus a1t1. We know the initial velocity is 3 meters per second. We plug this in. And we know the acceleration is minus 1 meter per second square. And we know the time is 2 seconds. So we can find out my velocity after 2 seconds is 1 meter per second. So I should have a dot here, which is 1 meter per second. And I know my initial velocity here is 3 meters per second. All right, so how about my velocity after another 4 seconds? We will do this calculation again. We're gonna calculate my v2 equals to v1 plus a2t2. So my v1 is my velocity at 2 seconds. So which is 1 meter per second plus minus 3 meter per second square, which is the acceleration from 2 to 6 seconds. And then times the time, which is 4 seconds, so I get minus 11 meter per second. So that means after 6 seconds, my velocity becomes what? Becomes minus 11 meter per second. So it's gonna be somewhere here. So I know my velocity at this instant, and at this instant. But in order to connect them, I need to know if it's a straight line or if it's a curved line. Let me use a different color to demonstrate this. So how do we know if it's a straight line or a curved line? We know that delta V over delta T equals to acceleration. But if you look at this velocity versus time chart, delta V is basically the change of Y, delta Y. And the change of T, delta T, is basically delta X. We know from math, delta Y over delta X is basically the slope. That means acceleration is the slope of the velocity versus time chart. And we know from this acceleration versus time chart, from 0 to 2 seconds, the slope is a constant, which is minus 1 meter per second square. In other words, from 0 to 2 seconds, there should be a straight line because the slope is a constant. and this slope is minus 1 meter per second squared. And similarly, from 2 seconds to 6 seconds, my acceleration is constant too, minus 3 meter per second squared. So connecting here and here, this should be another straight line, and the slope is minus 3 meter per second squared. So this is my velocity versus time chart. Of course, this doesn't look very pretty, so I plot them in a software, which looks much better, right? So what else can we learn from this velocity versus time chart? The key thing we discussed is acceleration is the slope, right? Acceleration is the slope for the velocity versus time chart. But also there is another important relationship, which is the area. So if we look at this area right here, clearly this is a rectangle. And if we want to calculate this area, the area equals to the base times the height. So what is the base? So this is my base, which is delta t. And what is my height? Which is my acceleration times a. But we know delta t times a is my delta v. So what does this mean? That means the area under the acceleration versus time chart is my velocity change. So if I plug into the value, for this rectangle, the time change is 2 seconds, and the acceleration is minus 1 meter per second squared, minus 1 meter per second squared. So the velocity change should be minus 2 meter per second. This is exactly what happened. From 0 to 2 seconds, my velocity decreased from 3 to 1, so it decreased by 2. And you can do the same thing here. You can calculate the area here. So the area for this bigger rectangle, which is my base, which is 4 seconds, and my height, which is minus 3 meter per second, minus 3 meter per second squared, which is minus 12 meter per second. So that means my velocity here at 1 meter per second should decrease by 12, which ends up to minus 11. This is exactly what I get. All right, so now we know how to get the velocity versus time chart from acceleration versus time. But can we get the position versus time chart? We can do the same thing. So let's plot the position versus time chart. We can say the initial position is basically 0. And we can also find the position at 2 seconds and 6 seconds. We have done the calculation last time, so this time I'm going to go much faster. So how to find the position at 2 seconds? We can use delta x1 equals to v0t plus half a1 t1 squared. We have done the mass, which equals to 4 meter. So that means from 0 to 2 seconds, my ball moved 4 meter, right? So that means my position goes to 4. So let's see, it's here, which is 4 meter. And we also know from 2 seconds to 6 seconds, we can calculate its displacement using the same kinematic equation. So v1t plus half a2 and t2 squared. And we know which is minus 20 meter. So that means after 2 seconds, the ball moved to the left by 20 meter. So 4 meter is its initial position, and 4 minus 20 meter, so which give us its new position, which is minus 16 meter. So it should be somewhere here. The position is minus 16 meter. So at 6 seconds, you should have a dot here, right? Which also makes sense because think about it. Initially, the ball is here, x equals to 0. After 2 seconds, it travels here, and the position is 4 meter. Then afterwards, it travels all the way to this side, and it travels what? Travels by 20 meter. But its position is from here to here, which is minus 16 meter. So everything makes sense. All right. But now here's the thing. The curve between this dot here and this dot here, is it a straight line or is it a curve? then we need to understand the relationship between displacement and velocity. We know delta x over delta t is velocity, and this is my delta x, which is the y, which is my t, which is the x. So in other words, delta x over delta t is basically the slope of the displacement, or you can say the position versus time chart. In other words, the velocity is the slope for the position versus time chart. And let's see if the velocity is a constant or not. You can see that from 0 to 2 seconds, the velocity is decreasing. Although it's positive, but it's decreasing. What does that tell us? That basically tells us the slope from 0 to 2 is decreasing. So that means it should be a curve, and it's curving down. So we can draw something like this. It's curving down. And as a matter of fact, for constant acceleration, this should be a parabolic curve. Okay? Alright, how about 2 seconds to 6 seconds? The same thing. The slope keeps decreasing. But more than that, in the beginning, the slope is positive. From here to here, the slope is positive. After this intercept, the slope becomes negative. So that means, if I use a different color, the curve should look like this. It should go up a little bit, then should go all the way down. And it also makes sense from this motion because at this moment the ball should still have some velocity. So the ball keep move to the east, then turn back, which is the position keeps moving to the east, then turn back. So this is the position versus time chart for this motion. And of course, I plot them in the software again, just to make them look better. Okay, so what else can we learn from these two graphs? Alright, let's look at the area. So if we look at the velocity versus time chart, let's look at this area right here. This is a trapezoid. We know the area of the trapezoid equals to the lower base plus the upper base times the height divided by 2. So what is the lower base, which is my initial velocity? What is the upper base, which is my final velocity? And what is my height, which is my delta t? And all this multiply together divided by 2. So that is my area. But if we look at this, what is the initial velocity plus final velocity divided by 2? That is my average velocity. So that basically says this area is average velocity times t. So what is average velocity times t? That is delta x. So in other words, the area under the velocity versus time chart is the change of position. In other words, is the displacement. So if we plug into all this value, my initial velocity, which is 3 meters per second. My final velocity, which is 1 meter per second, and divided by 2, and times delta t, 2 seconds. If we do the math, we got a 4 meter, which is positive. That means from 0 to 2 seconds, my displacement should increase by 4, which is exactly what happens here. From 0 to 2 seconds, my displacement increased by 4 meters. You can do the same area calculation for the second half. You're going to get the same answer. Alright, so let's summarize what we have discussed today. So first, we showed that the position versus time chart, its slope is velocity. And for the velocity versus time chart, its slope is acceleration. Okay, so that's the slope relationship. But we also showed that the area under the acceleration versus time chart is the change of velocity. And we also showed that for the velocity versus time chart, its area is the change of position. In other words, it's the displacement. There's one more thing I want to mention. That is, when you calculate the area, make sure that the area under the axis is considered as negative. That's all what I want to discuss today. Hopefully it helped you to better understand the graphs in 1D kinematics. Thanks for your attention. I will see you next time.